This video is going to be a demonstration of the Pythagorean Theorem using origami. And to do this activity with me, all you need to have is a piece of paper and 3 different colored markers. You can also use scissors if you would like, and if you have them around. Otherwise, you can always crease and then tear the paper instead. So the first thing we're going to do is create a square out of our rectangular piece of paper. So to do that, we just fold to make a right triangle. And then you can either cut off this remaining rectangle or you can crease it and rip it. I'm going to cut it off since I have scissors. Now we have a nice square that we can work with. And the next thing we are going to do is fold the paper lengthwise and widthwise. And now we're going to have a smaller square. And we're going to fold along that crease we already have to make another right triangle. And then pay attention to where you can see the edges of the paper. And from there, you're going to fold down to create any other right triangle you would like. So you can make it longer or shorter. The size doesn't matter. And then once you've bent that over, you're going to open the whole paper. And you'll see you have a square in the center. And from that square, you're going to bend the edges over and make very precise, crisp lines where the edges of that square are. So I'm going to fold my first line here, my next, and now what we've done is we've created a grid so that when we make our right triangles that we'll use to prove the theorem, we can be confident that they're all the same size. Now we're going to create 4 right triangles that are exactly the same size using the measurements that we've created with our folding already. So you're going to take this corner here, and you can see 3 lines in here, and fold over to make a right triangle. And we can see, when we look on the other side, we have a congruent right triangle, right? They overlap. Next, we're going to make another one, the same size. And we're going to turn and do the same thing again. And then you can see that we've created a square, and on the opposite side we have our right triangles folded in. Now we're going to do some labeling of our right triangles to stay organized. So I'm going to use pink for the short leg, green for the long leg, and orange for the hypotenuse. Now that we've labeled our triangle, we're going to unfold. You can see we have a square with a side length that is the hypotenuse of our right triangle. And now we're going to make a small cut along the short leg and fold back 2 of our right triangles. You can see we have 2 congruent right triangles and we're folding them back. And then we're going to turn and fold back 2 more of our right triangles. And now the area of the remaining space will be the same no matter which 2 pairs of right triangles I fold back. Now we can think about what this area represents relating back to our original triangle. So you can see now that we have a square the size with the side length of the short leg, and then the other square has a side length of the long leg. And if we relate this back to our algebraic representation, we call the short leg A. So this is A squared, the area. And we call the long leg B. So this is B squared. And we can see that when we fold it back and go out to our other triangle, had our original square, which was the hypotenuse squared, and we had taken away 4 of our right triangles to get that. So when we take away 4 of our right triangles in another way, grouped like this, 2 and then 2, we must have the same area for a squared plus b squared as we did for the hypotenuse squared, because in both cases we're removing 4 of our right triangles, 2 and 2, and then 1, 2, 3, 4 for our original square that was the hypotenuse squared, or as we represent it algebraically, the area of all of this is c squared.